So hello everybody, welcome to this third tutorial of the SAT+SMT school. The third tutorial speaker, it's my pleasure to introduce Amin Bere. He's the chair of, forget the group name. I know at Albert Ludwig's University Freiburg in Germany, but chair of computer architecture, is that right? Yes, chair of computer architecture. Prior to that, he was heading the Institute for Formal Models and Verification at the Johannes Kepler University, Linz, Austria, for many years. His research interests formal verification of hardware and software, building efficient solvers for SAT, SMT, QBF. His work has got a lot of international acclaim. His solvers have won over 100 awards in international competitions, and he has received the most influential paper award at TACAS, at Design Automation Conference, Test of Time award at ITAPS. So he brings here a very rich experience and perspective. In this tutorial today, he's going to tell us about quantum leaps and local search.
Thank you, Mina, for this kind introduction. So let me start like the motivation for this talk. So as I usually I give a SAT solving course in the summer, and this year because there were some sort of really unexpected improvements in local search, I thought to look at that. So I was teaching local search to my students, and I had them do a project. Okay, and you're going to do the project also in this last session. And it turns out is this local search where actually all these ideas around local search are one of the reasons of the sort of last big quantum leaps in the SAT solving business. And I'm showing you these leaps first, and then I'll explain both these kind of quantum steps. One is due to ideas from local search, and the other one is like due to target phases and so this is what I'm going to show. And last year, actually, there was a big difference, and this is my first slide here. So we prepared this SAT museum here. This was presented last year in Alghero in Italy. We had at the post workshop, so I'm looking forward to post workshop tomorrow again. It's my favorite workshop. And last year we presented this work, which is showing off the performance of all the winners of the SAT competition. So as you see here on the right, 1 year since actually 2002 when we started new competitions, but there's some more here, some earlier interesting solvers. For instance, here this one, which is a DPLL solver, which won the first competition in 1992, and the reason for this kind of work, which actually took quite some time, was because there were prominent figures in the community which said nothing changed in the competition since sort of like 1998, and this is like one of the reasons to show. One of the motivations was to show that this is not the case, and in order to do that, that's what I need to explain. Actually, we ported all these old solvers, like even solvers from the 90s. To modern operating system. This meant actually making them 64-bit clean and fixing some bugs because these guys had bugs, right? Most in the parsers actually, because some of them would, of course, I can maximum have like this one, this Böhm had a hard limit of 1,000 variables built in, right? Which is ridiculous these days. But it was easy to fix. And others had like things like as soon as you had an 8K buffer for the input. This was actually CRASP 8-bit buffer for the input line, right? And if a clause is longer than that, it would just truncate it. So these benchmarks became then very fast unsat, right? And anyhow, so we carefully fixed this all so that these solvers here are now the kind of updated fixed versions running on the same hardware from actually in Linz, like at the cluster where I was before, and which is now formally belongs to Martina, is sitting here, and this cluster is also almost as fast or almost identical to the star exec. So this what you see here is if you would look at the star exec, like the competition result, it would almost look the same. And you see here, sort of, we have here CDCL solvers, actually CRASP, which is here actually at the bottom. So note that, right? Like it's very down here. So it shows barely 10 instances. And then everything what Alex described yesterday kept on sort of jumping things ahead. So like, for instance, here we saw sort of this MiniSat jump, which is the biggest one we witnessed so far. And then there was this Maple and Coms PS jump, which was here. And then actually here in 2020, I contributed with KISAT to another jump, and I explained that a bit. And this has also to do with local search. All right, and you find way more plots along this line, even for different benchmark sets. So these were the benchmark sets from 2022, so 400. So here's no line, but you need to think of this as, here's the percentage of benchmark solved. Well, if this would be 250 over 400, right? And here's the running time. So this is the type of plot we're using for the competition now also. It's called cumulative distribution function, but only if you would have here like something between 0 and 1. But like if you know the total number of benchmarks, you get that. In the old days, until like 2 years ago, we used cactus plot where this thing was flipped on the diagonal, but we prefer now this one. And for various reasons, actually Holger Hoos has convinced us finally that we should use this one. So we'll see more of them. I think 5 more in this talk. So that's why I need to explain that. So you can think of this, you see, up to like 3,000 seconds, you will here see the number of how many benchmarks this particular solver solved with this time limit, right? Okay. So what about 2023? This was 2022, right? And you see another big jump last year, right? So there I don't have the nice plots yet because the paper there was from last year. But you see here another interesting jump here. Like here are these 3 solvers from which were running in 2022, 2021, and 2022, which were just variants of my version, right? These are down here. Okay, and then here, this is an old solver of mine, which is Cadigal, so it didn't win anything in the competition, but it would have won actually, yeah, last year compared to all these other ones. But there was another jump on top of this Cadigal, this SPVA Cadigal, a tremendous increase of solved instances. And this was due to this thing which you see there in front, which is SPVA, which means structural bounded variable elimination, and I'll explain this in detail. Actually, I'm not explaining the S. I only explain the BVA because this is actually the real thing. And it's very funny because we invented this in 2012. We had a nice paper in a best paper actually in Haifa HBC conference, and we never continued implementing this. And Marijn Heule, similar to what I do, so he gave his students this as an exercise. Re-implement this paper from 2012. Well, and here you see the result. Okay, so these were 2 master students who won the competition because they had like a very clever idea. I should say there's one thing you will see in a couple of slides. It's not just this EVES BVA. Actually, it's a bit true to the benchmarks. And it also actually explains a bit how this competition works. And there's an interesting debate now going on. So I'm really looking forward to the results this week because one could think the competition is broken, or maybe not, or maybe it's exactly not broken. So we'll discuss about this in maybe 4 slides. All right. So in 2022, check out, there's not this quantum leap here of this SPVA packetical, which is this black thing. Okay, so it improves on the catechol, which is the red triangle, here the black, a bit, right? But it's actually comparable to the KISATs. Okay, so what happened last year, right? On these benchmarks last year, this is what I'm going to show you. Okay, so this is the plan. I have, if I counted it right, like it's 1 hour 15 each part, and we're going to do these 2 parts first, and then at the end we're going to do an exercise on this second part. Okay, so part 1. So I already started with this, so competitions and quantum leaps. And I will focus on two things. I want to focus on bounded variable addition. This is this BVA thing I just mentioned. So remember that acronym for now, bounded variable addition. Before, and this is also what Alex showed yesterday, we had bounded variable elimination, which is actually responsible here for this gap here, for this first white gap you see here. And then actually, Alex already explained this a bit, this portfolio style, so which Jansik O invented for switching between two types of modes or phases, where you kind of focus on fast restarts and the other one you're not. And then at the I'll also present a bit on this target phases rephasing, because this is actually motivated by local search. So we have a technique which allows you to combine local search with the CDCL solver. And that will like spend some minutes on this one. Okay, then next session will be about local search, and I'll explain why this is interesting, why we should look at it. So in general, the idea here is I'm showing you sort of stuff where I think this is sort of a bit unresearched topics, right? Which would be interesting to look at. So I will look at this. So it's sort of, and it recently gave huge improvements. So maybe this encourages some of you to also look at this tool. All right. So just recall what bounded variable elimination was. So this is the old DP style of solving, which actually goes back to the 50s, last centuries. The only thing we did there in 2005 was this observation that you actually want to bound it. And what does bounding mean? Well, you see here 5 clauses, okay? And assume these are all clauses in which the variable x occurs positively or negatively. On the left, you see them occurring positively, on the right, negatively, right? So clause 1, 2, 3 is positive, and 4 and 5 is negative. Now, how can I eliminate the variable? Well, I just kind of do the cross product of all these. So this is a quadratic operation, right? So we see this later. So it's actually not that good, right? So if you can continue doing this, your formula will actually not double every time. It will actually grow quadratically every time in the worst case, right? So it's a very, very exponential algorithm for solving SAT. However, and this is the point, if you enforce that you're only going to do this if the resulting clauses, which you see here on the right, these are the resolvent, like you just do the cross product, 2 times 3 is 6, right? And you see here the numbers, like this first one is clause 1 and 4 resolved, like the first two here. Then this number of resolvents should not increase the total number of clauses if you remove the old one. So the clauses you add should be smaller equal than the number of clauses you had. Okay. And in addition, and this is was kind of an interesting insight, it occurs quite often here that some of these resolvents are tautological, like in this example, and so they actually drop out. So you kind of get sort of shrinking a bit. So it's not always the full quadratic product, right? That is also why you have to try it, right? So you try eliminating things, you count how many resolvents are non-tautological, and if this stays below the original number, then you just eliminate the variable, and then you continue with the all variable until nothing changes. This is bound variable elimination. And this is crucial for many industrial benchmarks. And so it removes actually formulas by 80%, reduces the formulas by 80%. All right, there's some part which I'm not talking about much today. We also figured out that actually during this process, you will get lots of subsumed clauses, and clauses you can actually strengthen by removing literals. And we also presented algorithms for that, but I will not talk about this here. It is the most important and most effective preprocessing we have. So everybody's doing that since like 2006. Okay, something which is new, and as I said, like we we invented this, got the best paper actually for this in 2012, but then we kind of stopped. And then the students of Marijn, the two master students, actually picked this up in the project and showed some remarkable results. And so what is this? Well, this is the opposite of what you do on top, right? Now the rule says you're going to introduce variables, but the resulting clauses should be less than the original one. And now here it's strictly less. Okay, because actually you want to combine these two. And so, right, this on top here actually kind of always goes to the limit, adding clauses, right? Clauses usually stay the same. Actually, they also go down a bit, but you eliminate variables. While here, you're introducing variables to reduce the clauses. And as we're going to see, this actually has quadratic effects in practice, in particular in hard combinatorial benchmarks. So how does it work? And I'll actually, most of the time I spent in preparing this, in explaining this in detail, so don't worry. So I'll go over that many times. So you try to find those patterns. So I think I kind of already have here kind of the pattern. So look at this A, B, C. So we're going to call them quotients, and these pink things, the magenta things, they're factors. And so you kind of need to find sort of these columns which have the same quotients, right? And they only differ here in the factor. And then if you have that, you can actually introduce a variable with like that. And in this case, actually you reduce the number of clauses by 1. And well, you see, this is what happened. So I just actually finished this 15 minutes ago, this run. And I forgot to produce it before. I was sitting in the last session. So this is part of this. I had already numbers, but this year with the new KISSAT I didn't have. So this is what I was running here. So what's this? Well, these are like 52 hard SAT competition benchmarks from last year. So how did what is hard? Well, very like personal opinion. Everything which KISSAT did not solve, but one of the others was solved, right? And okay, so this ended up with 52. And they all had, so I was complaining to Marijn and the others who selected the benchmarks. Actually, Marijn did not select. Well, they all look like pigeonhole problems. You probably have heard about pigeonhole, but we'll come back to this later. Yeah, and some of them were, like half of them are just pigeonhole formulas. So in a sense, this plot shows that, as further high you get, like with the techniques, they solve pigeonholes, except for this thing here. Okay, so this solves all but one. Okay, and this solver, this was by Yu Gao from Huawei, who also submitted the solver last year and almost won. Okay, so it was a version of KISSAT with symmetry breaking in front of it, and also PR clause learning. And he also submitted 20 benchmarks which nobody else solved except his solver. So this is the gap here. But in essence, kind of through this preprocessing, he lost actually against this SBVA old catechol. This is this blue cross here, okay, which won the competition last year. So in a certain sense, this is what the BVA gives you. So down here, you see my current version of KISSAT with BVA disabled. The old version would have solved just 2 benchmarks actually here. And these 20 benchmarks are like 30 benchmarks. This is this red and blue, sorry, red and green here. Okay, maybe I should show because these two. This is now what you get by adding BVA to KISSAT. And now I'm going to explain this. And it's very interesting that we have this idea like 12 years back, and the students kind of revived it. And this so this probably means that there's some additional ideas which could work here, and that's why I'm presenting this. There was another technique here, PR learn, This was also from CMU, but with Randy Bryant and other students. So they did PR class learning. And I think there was a Kate paper last year or 2 years ago where they proposed this preprocessor. And that also gets reasonable performance on these hard combinatorial benchmarks, but it's not as good as BVA. Yeah, this one here, the Huawei solver, right? This map prop here. This uses also like part of this code, but it uses symmetry breaking, like really classically symmetry breaking, where you look at for symmetries in the formula and add. And it's really surprising that you can do this strange PVA, revive it, and that you beat all these guys who do all these other techniques. And there was actually two more solvers, like one from Sweden and another one from CMU, who actually also try to kind of focus their new versions on hard combinatorial benchmarks. So altogether, there were like, it depends how you count, 5 solvers which try to kind of beat everybody else on hard combinatorial problems, like pigeonholes, okay? And then there was this competition, bring your own benchmark concept. They all submitted benchmarks for their technique where they would shine, okay? And now this year, we kind of had like all these hard combinatorial benchmarks, therefore added like more than 50. And this explains why there was such a big gap last year. And now, of course, the interesting sort of meta research question is, does this break the competition or did it not actually help us to find out that BVA is actually really cool to have? And yeah, I'm now convinced. I was shocked when I saw this last year, but now I'm convinced actually the competition is working. So this idea, so it has also a form of local search, and it shows like the value of this old technique, and we should invest more in that, right? All right. Before I explain now, or are there questions about this competition setup, like part, or about these results? Yeah, I forgot to mention these are, of course, always 5,000 seconds, like time. The time limit in SAT competition is 5,000 seconds, and that's why kind of in 5,000 seconds, with the time limit of 5,000 seconds, you can solve like 51 with the solver from Huawei. Yes, question? There's need the mic, right? Oh, yeah, these formulas are way smaller. Size of the formulas, what the question? These formulas are way smaller. I mean, I think there are a couple of big ones, like 3 or 4. So I really strictly only selected on those which are interesting from like a hardness perspective for my old version of KISA. So these are small formulas. And actually, for instance, this PR thing here, this only works on small formulas, while this BVA actually, as I'm going to show you, you can implement in such a way that it works on millions of variables. So this is also one difference. So with the symmetry breaking, I think this could also you can get it working on millions of variables, but with the PR one, you have to restrict it, say, to 10,000 variables or something. Otherwise, it's just too expensive. So that's the other part, which is interesting, that this BVA is kind of a robust technique. You can just add to the solver, and it works nicely. All right. There. Okay. The mic's coming.
Thank you. So the topmost SAT solver, the KeySAT with map prop, uh, is currently the best solver
No.
of all. No,
No, the
What is
best one last year. So we always every year on Friday, no, on Saturday there will be a new best one. But like up to now, it's until Friday. It's the one which won the competition, and it's this one here, the SPVA old category. This one with the blue and the crosses. And the reason for that is because that one was more robust on other benchmarks, on the non-hard ones. And in the competition, of course, both are thrown together. And there the top solver won, despite the fact that he solved 20 benchmarks uniquely, which actually the author of the solver submitted himself. Okay. Okay, for this hard benchmarks, is clearly this one is which you asked is the fastest one, but there's like this gap of 20, which is a bit cheating because it's some interval something, so benchmarks, which I also did not completely understand. He probably has additional technique in there which just solved these 20 benchmarks. Okay, and it's interesting also from the sort of meta research perspective, this didn't help him to win the competition, right? So this is very, very interesting from sort of like why competitions actually help here. All right, so what I want to do on this slide is to show you how this fits into this whole history of proofs, and maybe you haven't seen that. And also, I think Alex didn't talk about this. So there was we have I like a couple of years ago, maybe like 2020, I would have said what happened in SAT. So people ask me all this the time, and then I would say that well, the last 5 years we have proofs, right? So we insisted on proofs, and we have big proofs, and this is related to what I want to show, and so that's why I gave a very short presentation, like a history a list of results in this direction, and I often give just like 4 hours on all of that, right? So just it's very hard, and you find also tutorials from me on the web, even with videos. So let me like explain this a little bit. So most of you have heard about pure literals. So these are literals which only occur in one phase, right? And this goes back to the 50s. You can just remove all the clauses in which these pure literals occur, right? There's an interesting generalization, which is called autarky, which says if you have a partial assignment which satisfies all the clauses it touches, so all the other clauses are not touched, then you can also remove all the touch clauses. So it's just a generalization. And actually, Oliver, who promised to be here, but he's not here, has wrote a full handbook chapter on this already in 2009 without any practice yet. And then actually 2 years ago, we implemented actually his algorithm, which is between two lines of the handbook chapter, and it seems to work. Then, of course, also what you know, probably subsume clauses. This is an old idea. So if you have a clause which is shorter and you have a clause which is longer but contains like more literals than another one, you can remove the larger one, right? And there's a variant of this which allows you to remove single literals from a clause. And this was already in this paper from us on bounded variable elimination. And now comes another actually invention of Oliver's, also proposed here like a clause elimination technique. He called it block clauses. Actually, he didn't have the motivation to use it as an elimination technique. So you see here on top of the slide the word elimination and addition. So he actually proposed this as an addition technique. So block clause is a clause you can add, and it has a similar effect as kind of symmetry breaking. It actually reduces models, but you're allowed to do it because it has some kind of without lot of generality. I can assume disorder, right? And this has helped him to reduce sort of the running time of worst case running time on some 3SAT instances. And then actually in St. Andrews, I didn't know about this work. Marijn explained this to me on a bus. So it's always good to have these social events at that actually these block clauses are allow you to simulate lots of things you actually either would do when you encode formulas. And so that's why we looked at this and came up with this block clause elimination in 2010. And we first thought this is really cool because you have another like subsume clauses. You remove clauses from the formula, which is a good idea. And this was our first intention. But I have to say, and we also, of course, implemented this and fast, right? It doesn't help at all nowadays. It's actually negative for today's solver. Like in the old days, like back in 2010, we really had graphs where you solved a bit more instances. But nowadays, it's actually bad. And maybe some of you know this Play-Stil-Greenbaum encoding, which you take monotonicity into account. It's also bad. And it's actually simulated on the CNF level by BCE. So we introduced this for kind of a completely different purpose and claimed it's cool, right? But it's actually not anymore. But it triggered all this other work you see here, right? So it's very funny also how research work. In particular, we then continued. We added new like variants of this, right? So we added more extended versions and whatever. And in particular, this one is worth mentioning. This 2000. So I need to look here. The 2012 version here, too far away. This 2012 paper, the red. And this was the paper where we introduced this in-processing in SAT solvers, because this proof system became the default proof system for the SAT competition, and it has been used since actually then. And then we had this co-supervised student. Actually, Martina was the formal co-supervisor, but Marijn and I worked with him, Benjamin Kiesel. And I still remember where we stood in the front of the whiteboard in Linz, and like we just draw something, and even we don't know who drew this first. So we drew this rule for the PR classes, and then we sat down and said, okay, now we finally found the most general version, okay, and we started it. So this is now called propagation redundant, and this PR is actually what I explained to you before, like this overuse, this PR learning, like okay. Here is another not useful technique. It's called globally block clauses. Then in 2019, actually, which I I still found really impressive. Like two theory colleagues, Neil Tapman and Sam Bass, came up with a generalization of our PR here. And this paper is a theory paper, proof complexity paper, and showed that this variant, it also includes like symmetry substitution. Actually is able to, so this proof system is able to give short proofs for all the known examples in the proof complexity world, which was kind of very amazing to us. Actually, I think there's a paper, they're not here yet, but in the SAT conference, where they show that this thing is actually more powerful than extended resolution, which is, I'm really looking forward to this paper. Then related to this, Jakob Nordström and others are proposing here this very PB-proof system. I think Bart is here, right? You're also pushing this one. So the PB stands for, it's not another acronym for something, it stands for pseudo-Boolean. So they lifted these ideas we had here to another constraint format. And last but not least, actually, we presented, we showed how you can extend this to incremental proofs, which are, of course, very important because, as we discussed yesterday with Alex, in industrial applications, you mostly have in incremental calls to a SAT solver. So this increases the trust in industry and also in competitions. So you hardly have kind of what we call discrepancies, solvers which disagree whether something is SAT or unsat. Actually, industry picked this up. So Amazon is a good example for that one. So they really run SAT solvers and SMT solvers in big scale, and they want to have proofs. So they want to have proof checks. But there are other companies who really do this, like Sisterel was an example, who actually already since 2016 engaged with the SAT competition and the community because they require to have proofs for their railway interlocking verification software in France. So they really need proofs, otherwise would not be allowed to that this verified controller is really verified. Okay, and then last but not least, there are these spectacular math results with SAT solvers. The first really big one was this Pythagorean triple problem in 2016. Now, you see, and all the practical part, so this was theoretical here, was about actually removing clauses. Well, here, I mentioned that this paper here, for instance, it added such clauses. So these clauses remove models. So you shrink, like symmetry breaking, you shrink the satisfying assignment, but you do it in such a way that it doesn't make the problem like adding these clauses into an unsound process. And but all these attempts were mostly manual. So in this paper, for instance, they came up with manual proofs for all this hard complexity. And you saw also on the previous slide, so these PR clauses are not really working that well in practice. And so the question is, how do you add? You turn this kind of around, so you kind of want to add sort of stronger clauses which remove models, but are still sound to add, and you want to do this in a kind of a practical way. And there, the only thing which is currently working is actually this idea of DVA. And we need to kind of find new, better ways of doing this. It's also kind of the only way where we have like practical results on extended resolution. All right, and so this was pretty abstract. For those of you who know block clauses, this will be boring. For the others, it will be too fast, but I'll nevertheless try a bit. So I need to tell you that I looked at this when I first saw this definition in 2010. I looked at it like one day. Next day I said, oh no, it's not, can't be true. Then I looked at it the third day. I understood it. And then again, I woke up, no, that can't be true. So that's why I don't expect you to, if you haven't seen it before, to understand this. But like maybe you get a flavor, get an idea how this works. All right, so what's a block clause? Well, there's a formula, F, and you have this clause C, and this clause is kind of redundant with respect to the formula, so you can add it or remove it, right? So this is this adding or elimination. And then here's one criteria when you're allowed to do this. And so you pick a literal in the clause, so only one. This is when I first saw this, I didn't believe that one is enough. So I thought you need to show it for all of them, but you only need to show it for one. So this L is fixed, okay? And then you consider all the clauses in this formula, which potentially can be resolved with this clause on this literal, right? So these are all clauses which contain a negation of this literal. But once again, you need to fix this literal first, right? And then only for that literal, you look for clauses in the formula which can be resolved against that one. Okay, and then this clause is blocked if in this situation, this resolution of C on L with all these candidates would always result in a tautology, right? Maybe remember when we did this variable elimination thing, like there were two clauses which were tautological. Here you require that all of them are tautological, but for one clause, right? Then you can drop this. And there's one intuition which why this is true it looks like if you have this situation, you cannot really use the clause in a resolution refutation, right? But it's actually not that easy to see. And here's like an example first, and then I'll show you in the next slide a formal proof, which I will really go fast. All right, so how does it work? So what you see here are three AND gates encoded into CNF. And I hope most of you have seen SAT encoding. So here's like X is equal to A, right? So you see this clause 5 here is doing X implies A. This one says X implies B. And this guy says if A and B is true, then X has to be true. This is simply X is equal to A and B. Then you can do the same here on the right with Y is equal to Z and X, right? And here is not C is equal to A and B. So this is actually a NAND, if you think about it. Like C is the NAND of A and B, right? Now, is this SAT? Well, yeah, you can think. It has kind of a cyclic flavor, right? But now we're going to show that it's like SAT by just using bound block clause elimination. So first, check out here this clause, okay? And we see that this clause Y here, and this is always the case, and actually only occurs here in sort of these other gate clauses. So these are the gate clauses, right, of Y. And then actually this happens by the default sitting coding all the time. If you resolve these clauses, then you will get a tautology. This is just by definition, right? Because here they occur always in the opposite polarity, right? So resolving this clause on Y with one of the other two gate clauses gives you both a tautology. So block clause now tells me I can drop it. Okay, and now after you drop the red one here, you realize, oh, now not Y is a pure literal, which formally is also a block clause on this pure literal all the time. I can also drop them, right? Then the whole AND gate here is gone. Okay, and now the same thing happens here with the X, right? because for the same argument, right? So the x occurred here, right, to the right, but this clause is now gone. And therefore, I can also like completely ignore like the rest. And I know that these gate clauses resolving against each other on the gate variable will just resolve in tautologies. So they're also gone. Well, and then what you have left is one final NAND gate, and the same argument applies, right? So all clauses go away. Well, the formula is SAT because it's just true. Now, how to get back a model, right? So now you have a formula which is true, which satisfies this gate constraint is an interesting problem. And it's very technical and has a very beautiful solution due to Niklas Sørensen, which he did not publish, but Matti and I wrote it up. And it's, of course, implemented in this all these preprocessing solvers. Okay, example clear? All right. Here's the proof, and maybe before I will go through the technical part very fast, but like the large bold one here is the most important takeaway. So how do you prove now that this is, yeah, of course, now we have to be precise with respect to completeness and soundness. So, so here I show BCE, block clause elimination, is complete, and you do this if by showing that if the original formula is satisfiable with this clause, then you can drop it, and then F is satisfiable, right? Sorry, I should have been the other way around. So I think I did a copy. So it should go. Sorry about that. It's the other way around. If F is satisfiable, then F and C is satisfiable. Okay, sorry about that. Because this is also my assumption in the third line. So I just didn't pay attention. All right, so assume F is satisfiable, okay. And of course, we have the side condition here, right? So apologize, this should be the other way around. So assume F is satisfiable, and you have that. So you have a model for it. But now, and this is the only thing you kind of need to show. Assume that this model you have for F is not a model for C, right? Because if it would be also a model for C, right, then the reverse direction would hold, right? Okay, so this is the only case where I kind of need to fix something. Okay, I have a model for F, but I don't. This is not a model for C. So what do I do? And now is the idea, and this is that this sigma prime here is the same as sigma, but you just flip the value of the literal L of this single literal on which you block the clause, right? You just turn it from 0 to 1 or from 1 to 0. Okay, and then you have three cases, and these cases are technical, but let me point out again this thing here. Okay, in this particular situation, you see the only case where sort of now flipping this literal would break something, okay, is when actually this literal would occur negated in another clause like here, okay, because then it's true and might satisfy this clause, right? But by flipping it, I turn this literal here to false, right? This not L, I turn it to false. I need to check that this doesn't really break satisfiability of the sigma prime. Well, and now the observation is due to this condition of block clauses, there has to be another literal, like the one where you have the clash, okay, another literal K in this D, which in opposite phase in the C, right? Because this was our condition that if I resolve on this L, I find another literal, which in the original clause is an opposite sign, right? All right, because of this condition, it's in the clause C, right? So it means the K is C, so it's false, but it's in opposite phase polarity in the D in the resolution candidate. So that's why it's true there, right? And that means this clause is actually under this sigma here, double satisfied. So all the resolution candidates are double satisfied if you have this condition here on top that the clause is blocked and you satisfy the original formula plus you falsify the clause, right? So you can just modify it. And this is kind of the insight which actually invariant is in all these other like more complicated versions you see. So that's why I want to take you away. You can of course work through this proof, except that the first line was wrong. That double satisfied is kind of the insight which actually is behind this the correctness of these systems. And of course, soundness here, and of course probably I flip this here again. The then should go in the other one. Is then just the opposite, so it's just by contraposition. Okay. So you can add these clauses or remove them, which are blocked by these comments. And now we get here to um, this interesting first result that, of course, extended resolution is just block clause addition, right? So in case you know extended resolution, that means you're going to add such a definition, x is equal to a and b, where a and b are existing literals, and x is a new variable, okay? And you can just add this to your formula. This, of course, doesn't change sort of the satisfiability status of your formula. And with this extension rule, you can actually get exponentially smaller proofs. And why? I mean, like Cook showed this for the pigeonhole thing, but like my intuition is the following. Well, with this extension rule, right, you can simulate what this computer is doing. Like, because, well, I'm professor for computer architecture. How does it work? Well, there's a processor which works with bits, right? And every computation in this processor you can actually define by just adding gates. So anything what this computer actually can do can simulate by the extended resolution, right? Everything, right? Like even like higher order of theorem proving. It's really true. So that means you can. This was the sort of this my argument why extended resolution is the most general thing actually out there. But well, this week we'll learn there's SR, which is actually more powerful. Okay, and block clause addition can simulate this too, right? So with this simple thing, what we just discussed, both in practice, you can simulate the most powerful proof system. Well, except that we're going to have an update this week. Okay, and then we added these two ideas that you can actually sort of, the tautology is not immediately apparent, right? You need this tautology when you do the resolvent, right? Then you get a block clause. But actually that the resolvent is kind of implied by the formula. And being implied by the formula through unit propagation is called AT, like you just take the negation of the clause, you propagate. And if this results in a conflict, you say the clause is AT. And then this RAD is just the same as block clauses, except that you replace this tautology condition by, well, the resolvent is unit implied by the formula. And this is what we have been using in the SAT competition since like 2013. Okay, and the reason I'm showing you this finally is because this also shows how you actually simulate the BVA step in this example we had with the RAD, which is necessary because otherwise this would not have been allowed in the competition, because the competition requires that every solver, all the techniques you have there, you have proofs. So you need to have a RAD proofs for this example. And so how does it work? Well, all right. So I have here the numbers, right? So the clauses on the left are original clauses in the formula. Okay, then I'm adding here this positive, this are my quotient clauses, right? Why? Because they're pure literals, right? I can just add them. Just pure literals. I can add, like when I have a new variable, I can just add clauses with this new variable. And of course, they also blocked. Okay, now comes, I add 4. Like these are my two factor clauses, like they correspond to these columns here. So why can I add them? Well, if I resolve this D here, so this clause 4 here with any of these clauses here on the left, like let's say for the first one, right? Then I still have, of course, these clauses here in the formula. I didn't remove them yet. And you see this just gives you these two resolved just gives you this first one, this 6, right? So it's actually implied, right? It's subsumed. So we have a weaker version of red, which just looks for subsumed clauses. Okay, so you do this, all three resolvents here on this first one would always find like one of these subsumed ones, and the same is true for the second factor clause, would find sort of subsuming clauses here. Okay, so that's why you can add those guys through red addition. Okay, now why can I drop the original clauses at this point now? Right, so after I've added this, why can I now drop them? Well, this is even more trivial because they are all just unit implied by this right form. For instance, if you take again D and A, you negate it, you say D is false and A is false, you plug it in here, you get immediately a conflict. You say X and not X, right? And so that's, you do it for all of them and you just can drop them. So this is how this BVA is simulated by RAT. All right, now something which occurred while I was writing this up is maybe some people are like know about synthesis, hardware synthesis, circuit synthesis, except Alex. But all right, so espresso or like two-level synthesis, Quine-McCluskey. So that's like where you have these polynomials, right? So this is what I'm teaching actually first semester. So this is like a two-level circuit, and you try to minimize it. So this is the task. And in the old days, that means in the 80s, they already had this concept here, which they called algebraic division. And it actually does exactly what we want to do with BVA. So it's kind of what we did with BVAs has actually a predecessor, which is very similar. And I show you this simply here by this two equations, right? So this is like our two-level sort of DNF we start with. Okay, in hardware, often you drop the AND, right, and the plus is an OR. But you can think of this as in algebra, like multiplication and addition. And well, then we can take two of these terms, cubes, and try to get like factorize it, right? So this is like BC here. I can factor out BC, and A plus D remains, right? And oh, I forgot the CE. Another bug. Sorry about that. So there's a C missing here, and the CE as rest remains. So this doesn't have a. This does should be a C here, right? Or you can just factor out the C. This is why I had the C of all of them. C occurs in all of them, so I can just. And now this, think of them as circuits on the right. They're like 3 levels. They're not just 2 levels. They're 3 levels. And okay, and I claim that that's exactly what we're doing in BVA. We're trying to kind of, in hardware synthesis, of course, it's about like decreasing the size of the circuit, right? This is for area. It increases the delay, but like the area, shrinking the number of transistors you need to implement something. And for that, they use since the 80s this algebraic division. Now, why is the same as what we do with BVA? So let me first give an example here we had on the previous slide, but as a polynomial, okay? Well, you see, like this looks really the same. So D plus E, you multiply out. It's exactly what you had on the previous slide. And if you don't believe that yet, well, just look at the CNF. It's just like in Boolean algebra, like multiplying out distributivity law has 2 versions, right? So that's why everything you can do here, you can do here too. So the only interesting thing here is that, yeah, this dot here, right, which gives us the 3rd level in the circuit, that we can, of course, not have if we do C and F. So we need to kind of get rid of this 3rd level. And we do this simply by introducing a variable, and I show you it here how it's done, right? And this is our SAT version down here. Well, you just take everything which is here for the left quotient, right? You put an x to it, and here on the right quotient, you put a not x, and you quantify it existentially. And of course, in SAT, this existential quantification just goes to the very outside. So, and this is why it's really the same concept. It's exactly the same. So all the algorithms which they invented in the 80s, in principle, should work for us and also the other way around. Of course, I got excited after I figured it out, and I went to the literature to check, do they have better algorithms than we have? And of course, they didn't. It was also the 80s because they didn't have big computers, and yeah. Okay, but it's interesting that this is a similar concept, and maybe there's an interesting, maybe somebody finds some old papers where kind of we can use some, insights for improving this BVA. All right, so for the last 15 minutes, I have now an extended example of this BVA, and this is the one we had on the slide. I'm doing this now in Dimex because it's way harder to do this with real variables. And I hope all of you know Dimex, right? Who doesn't know Dimex? Anybody? I hope everybody. Oh, there's one who doesn't know Dimex. No, you're joking. All right. So Dimex, everybody knows Dimex. And then remember the color code. I hope nobody is colorblind, but otherwise I'll explain how you detect it nevertheless. So 3, 4, 5 are the quotients, right? And then we have these numbers which are the same for all the quotients, right? And this is one factor, and this 2 is another factor. Actually, this terminology factor and quotients, that's what I use in my implementation of this. And I think like this is a good way to explain it. So that's why I want to show you this too. All right. Yeah, here color is missing. Sorry about that. All right. And then you can have 3 columns. You can have 4 columns, right? And how does now BVA work? Well, as I said, you copy kind of the quotients, right, with a new variable, right? This is a new variable, like variable number 6, and it keeps the quotients. And then you take the negation of the variable, and with one always like for each of the factors, right? So like 1, 2 here corresponds to these 2 columns. So this column compares to these 2 columns, and then with 3 columns with 3 factors, right? Just these 3. And with 4 factors, so this thing gets just to 4, right? Clear? Okay, and then you also already see, well, yeah, so as bigger sort of these patterns get, as more clauses you save. All right, now comes the interesting part, which I spent most of the time when preparing this talk, because back then, already in 2012, we showed empirically only that at most one constraints are really interesting for this BVA. So I don't know, most of you know at most one constraint. Most of you played Sudoku, right? Actually, later we're going to do encode one of the constraints in Sudoku, which would be like at most one constraint over 9 variables, because you can only put kind of like 1 or 2 or 3 or 9, but at most 1 into one field. Okay, and then this one would be, it's encoded as at most 4. Actually, if you pay attention, Dimex, it's actually not at most 1 true, it's at most 1 false. Okay, so why is that? Well, this formula says, well, 1 or 2 have to be true, 1 or 3 have to be true, 1 or 4 have to be true, and then 2 or 3 have to be true, 2 or 4, 3 or 4. So you see, this is like 4 over 2. Right? So kind of all pairs of 2 variables, at least one has to be true. And this says at most 2 are false, actually. And I do this because otherwise my whole slides would just have redundant minuses there, right? But it's kind of at most 1 false instead of the usual one where you would say at most 1 true. But it's of course the same concept, right? Okay, so I hope you're with me with this. So this encodes at most 4, okay, with this flipping of the sign, right? Okay, and here you see, I find a pattern. Yeah, 1 column, another column, 2 quotients. Okay, 2 factors, 2 quotients, and if I re-encode it here, well, I don't gain anything, right? I just introduce this new variable, and yeah. Well, turning it around, if you see this situation and you have kind of a variable occurring twice positive and twice negative, variable elimination, you should always do it, right? Because 2 times 2 is 2 plus 2, right? So that's why actually it's clear that this is like not giving you anything. But here, if I now go to at most 5, and this is kind of also explains a bit these encodings, then suddenly you get 1 clause less, right? Okay. So again, we have here our full at most 1 constraint, right? So it's always a triangle. Okay, it's n over 2. So 5 over 2 is 10, right? And so 10 clauses and 5 variables. And I can re-encode this like that. And I save a clause. However, so keep this right example in mind. So I have it on the next slide again, on the left, okay? It's called A because there's a version B, and then you already see there's interesting things going on. Well, you can factor it like that, okay? This means 3 quotients and 2 columns, or you can do the opposite. You do 2 quotients and 3 columns, like 3 factors. Okay, and of course it gives you different factorizations. And of course you need to choose one. And of course I'm choosing the first one somehow, but there's some heuristics, and this is actually the place where I think like there might be new things, interesting things lying around. And also the two students of Marijn, actually, they found one interesting way to kind of which one of prefer. And that worked for these Ramsey problems Marijn is looking at, while the default did not work, okay? All right, so let's play this with Sudoku, okay? We're also going to play Tetris now, so Sudoku. Why is this Sudoku again? Well, this is 9 variables, right? Right, so you in Sudoku, if you encode the Sudoku into SAT, so this is like a standard sort of like first semester logic exercise now, you will actually have constraints like this, right? Like 36 variable which rule out pairs of numbers. And then of course you have it for each cell in the Sudoku. So this is, right? And clearly, this is the point. If you just pick the first column, you don't gain anything, right? Sure. Actually, you get, and this is introduces the formula you need for this. And I mentioned it before. It's just the number of quotients times the number of factors minus the quotients minus the factors, right? Obviously, right? If you think about it. So if you think about the process, how this BVA works, you're adding Q clauses for the quotients with the new variable, and F clauses for the factors. And this is, if you do the math here, you actually would add 1 clause, and there's no reduction, -1. All right, so now I get this reduction, right? If I do 2 columns. And how do I get here from here to here? And this also explains the algorithm. So I don't have a pseudocode for the algorithm. Well, you pick first the variable which occurs most often, let's say 1, okay. Then you go through this kind of quotient clauses and try to find common variables to all of them. Or to actually, you count how often do other variables, not one, occur in these quotient clauses you picked so far. And then 2 would, for instance, get here, what is it, 9 minus 3 plus 1 would be 7, right? Okay, and this is why I pick 2 as second factor. Okay, by this simple recipe. Okay, and then after I've picked 2, I need to, of course, remove this false clause here because this one doesn't have the 3, right? This clause here is missing. Okay, and so I need to remove that clause, and I get this block. And I think you see how this is going on, right? So like now I do the same, and then I will find 3 has many like quotients in common with these guys. So I have here the quotient clauses of the last column and try to find like variables, in this case 3, which occur often here. And there will be 3 here. And then I pick that one as next one, and I get again a reduction. And if you do the math, so before we had 5, right? And now it's 9. Right? Because it's 6, 8 times width minus the sum of the 2. And one more, and then you study, oh, it's increasing, right? So now it's, this is even better. Well, because, well, you can even probably see this already. You want to have here, for this at most one constraint, the 2 factoring quotients close to each other, right? And this maximizes kind of the area covered by this rectangle. And all right, we do one more, and surprise, there's another 11, right? Well, obviously, right? It was 5, 4, and now we have 4, 5. And you see how it goes. Now we get down to exactly symmetrically because this at most one constraint is a completely symmetric formula, right? And so it goes down to 5 again, and then at the end we'll have again -1. So when do we stop it? Oh, my call dropped, sorry. All right, then I'll need to, yes, I need to get to this theme. Now I have it here. Wireless, sorry about that. Yeah, I also don't know. Oh, yeah, it seems to sign in. Okay. Yeah. Okay, advanced. For this one, the next one, but for the last one, I need, yeah. It's a English, sorry. It's an English keyboard. Looks German, but it's an English keyboard. So do you have a Ethernet? Well, I could use an Ethernet. So one way would be to just disable the Wi-Fi completely and then maybe try it again. Okay, and then connecting, right? Yep, worked. So somehow, okay, now you clean, I need to get the, and switch of cameras, switch of micro, and tile. Working? All right, so what you missed, I don't know how long this went on, is that we went through this at most one constraint for 9, which is in Sudoku. And now we knew that, yeah, now this was the best reduction, right? With actually the first best reduction with the 5 times 4, right? 5 quotients and 4 columns. And if you do those reductions, so I placed this inside here of the existing one, you see clearly an improvement. Well, 11 clauses go away, right? So you reduce here from 36 to 25, right? And remember again the structure, right? So this is exactly the reason I'm showing you this is actually very simple. So just take the quotient you found, right? This is this quotient here, and then for each of the columns, you add here like 1, right, with a new variable. Okay, and then we're going to play Tetris, right? Right. This is what I promised. Okay. So all these things move now to the left, and we continue factorization. Here comes the interesting question. Okay. Can you look at this and figure out? By now you should know the algorithm. Can you? Is it useful? You see, if there would be 2 by 2, it's not worth. It's worthless, right? So can we do more? Yeah, somebody's nodding. Yeah, there's like a 7, 8, 9. I'm sorry, even a 6, 7, 8, 9, right? So this is the maximum. So we would now need to do the same thing. So, and again, the algorithm would be as we saw before. So maybe 10 is actually the most occurring one, or 5, and so. And by the way, this is also non-deterministic, unfortunately. So, but you just take the next variable, which occurs most often. You do the same algorithm again. Okay, and this is 4 times 2, so this is really good, right? Like 2 times 2 is the bad one. And this is another one. This is 3 times 3, and we're using that one because this is better. Okay. And we're removed 3 clauses, right? So this was 25, and these 3, and we do Tetris again. Now, can we continue factorization the third time? Now it becomes really interesting, which I also I don't have any intuition about this, but it's actually working. So it's a bit odd, as you will see. Yeah, there's another one. Like you need 3 columns, right? Otherwise, 2 columns is not enough. And so these are like as before, but these 2 alone would not allow me to reduce further, right? We discussed this before. But you see, there's this strange thing that this was a new variable, and now this one occurs as a factor, right? With also these 3 and 4. Okay, because we factor out those guys again. So we kind of factor out things, and then we factor out in the factorization again things. And of course, if you implement it, you don't care, right? You just go over the next largest variable. And so this gives you then this solution. Now I don't know. So now I wanted to show one demo, short demo. It's just on time for the break. Can I do this? The technicians. It's just like I need to. It's just 1 minute. No, just because of the technical side. No. Okay, I'll do this. And now let's see Tetris, right? And what actually my implementation would do, right? So you can download the latest KeySAT and apply it to this original program here, formula at top. What would it do? Well, let's try. So it's to the demo thing, and then there's this pigeonhole 11, right? So not sorry, this is not the right one. I need to go to my talks, advanced talk factor, and there's this AMO 9 CNF, right? This is the one we had here on the slide, and now if I do only KeySAT as a preprocessor of this AMO 9. I get exactly the same numbers we had there before. Okay, so there's a 13 there for some reason, which is a bug in KeySAT, but this should be 12 for some reason. All right, but you get the point, right? So actually, somehow my implementation did exactly what I did manually here on the slide, and this is probably due to the sort of symmetric, balanced thing of the BVA, which of this at most 1 constraint. And now the surprising effect of all of that is that this really does some kind of re-encoding of at most 1 constraint from a bad encoding, the naive one there on top, into something which is actually square root kind of better. And this almost concludes this part. So I'll have one more slide on the square root thing. I generated here, like for different Q and F values, right? The table. And then I have here, for instance, oh, sorry. I have here, um, this was our trace we had for this at most one for the Sudoku at most one, right? And here's like just an artificial one, right? So this could happen, right? So you always go one to the right, right? But actually you can stay there, right? So for instance, you could have two and you can extend it by two and extend it by another factor with two. So this is why you have your horizontal moves too, okay? But you always go to the right. And it's completely clear that, well, you can have here maximum and then get smaller, right, again, but later have another maximum, and you could even go here, right, and have further maximum. So this sequence of numbers actually could have an arbitrary shape. So you should actually try all of them. And then worse, okay, this is highly deterministic, non-deterministic, right? Which variable you pick, in which order you do the other one. So, and of course, you want to maximize this number. So it's a challenge to come up with algorithms which do this best. And then you also see that well, you almost get to square root, right? So this is approximate square root. As bigger this get, you actually reduce formulas by square root. And there are benchmarks in the competition which have like 10 million binary clauses, and you do a square root of this with this thing, right? This is really quite impressive. So this concludes my first part. If there are questions, I'm happy to answer them in the break or later in the next session. So thank you for the first part. Yeah, sure. I don't mind. It's for the organizers to decide.
So my question is, you showed examples with binary clauses, but only with binary clauses,
Yes.
right? But it
So
should work
yeah,
with larger
yeah,
clauses, right?
yeah. I wanted to give this comment earlier, but I was running out of time. No, this works exactly the same way for larger clauses. The only difference is then that these implementation-wise, it's way harder. So this one part, this what you saw already gives you like almost everything you saw in this improvement. For if you only do it on binary clauses, it's very simple to implement. If you don't have binary clauses, you would have, for instance, here 1, 3, and another one, right? So this quotient clauses would be ternary, and then we need to find, like here also in the second column, the same, let's say, two literals. But it works actually same ways. You just go through all these clauses you selected in the last column, right? And then you go into you try to find clauses which have one literal different than the quotient. Okay.
But in your implementation, you have only binary clauses by default now, or
Yeah, so the solver has this option to say binary clauses, but like as I said, 10 of these 30 which are solved by KeySAT cannot be solved by binary clauses only. So you really need the full one, and it's actually not costly because it rarely doesn't happen that often. Yep. Okay, then.
Any further questions?
That or
Yes, in
also
KeySAT.
SBVA.
No, this is now implemented in KeySAT, and so you can download it from the latest version. It's in the competition, or it was running in the competition, and it solves way more benchmarks now, of course, and as expected, and you can play with it. Maybe I should actually from the demo show you. This is what I wanted. So this thing here, this KeySAT BVA only, is a small script which just disables certain things. Like it would have a preprocessing. It will not do any backbones. It would stop after conflicts, will no concurrence closure, doesn't do lucky phases, and no fast elimination. And then the only thing which remains is bound variable addition. And then so you do this, and then you stop, and then you print it. That's this -O. Okay, so you can play with this if you want.
Thanks.
Okay, thank you.
Yeah, we are breaking for lunch, and whoever has given special request for food like Jain food, vegan, please contact the staff there. Okay. Again, the lunch is